Okay, today we're going to look at hypothesis tests for two proportions. It's probably going to take a couple of videos. It's a longer process than the confidence interval. And there's some tricky things that are going to go on in the mechanics that we'll have to take a close look at. So let's just dive right in. A study published in an Archives of General Psychiatry examined the impact of depression on a patient's ability to survive cardiac disease. Researchers identified 450 people with cardiac disease, evaluated them for depression, followed the group for 4 years. Of the 361 patients with no depression, 67 died. 89 patients with minor or major depression, 26 of them died. Among people who suffer from cardiac disease, are depressed patients more likely to die than non-depressed ones? Okay, so we're wanting to compare two groups, a depressed group and a not depressed group. First, a little throwback to Unit 3, what kind of design was used, so we'll throw that in to be reviewing old material as we go. This is an observational study. So they picked some patients and then they followed the group for 4 years. So they picked them and then they watched what happened. So that's a prospective study. It's a term we haven't seen for a while. Prospective is when we pick them and look forward, pro. Retrospective is when we pick them and then look back at their records at what has already happened in the past. Okay? We need to write appropriate hypotheses, and we always want to make sure we define each population. So there's actually two populations here, depressed people and not depressed people. So I might want to pick subscripts that help me keep up with which one is which. So let's let P hat for D be our depressed people. So the percent of depressed who we're trying to find out if they're more likely to die. So it's the percentage of the depressed people who die. Okay, that's considered a success, even though ideally that's not really successful, but that's how we want to attack this problem. And then P hat of, let's say, N for non-depressed. So P hat sub N is the percent of non-depressed people in the study. Well, no, non-depressed people in general who die. So we know who died in the study. We want to make some sort of a thought about everybody who is depressed and dies or doesn't die with cardiac disease. So after we define our P hats, oh, these are not hats. These are P's. Mark those hats out. This is a statement about the entire population. So these are just plain old P. So all people who are depressed who die, all people who are not depressed who die. We don't need to do a test about the sample. We already know what they did. We're trying to run a test about the population. Okay, so null hypothesis is comparing these two groups. Now, the null hypothesis always assumes that the two groups are the same. There's no difference. One is the same as the other. So the difference of the two groups, P depressed minus P not depressed, the difference would be 0 if the two groups had the same rate of death. That's always your null hypothesis, that the difference is equal to 0. Your alternative hypothesis argues differently, that the difference of the two groups, P of depressed minus P of the not depressed, isn't 0. Well, let's see if it's a not equal to, a greater than, or less than. In the stem of the problem, we're asked if we have evidence that depressed patients are more likely to die than non-depressed ones. So if the depressed ones are more likely, then the D should be a bigger percentage than the N group. So a bigger number minus a smaller number should be bigger than 0. So that difference should be greater than 0. Null hypothesis always is difference equals 0. Alternative is difference is less than, greater than, or not equal to, depending on how the problem is phrased. Okay, step 2, check your conditions. They're exactly the same conditions that we checked for the confidence interval. So I'm going to roll the first two into one. I need my groups to be independent, and I need them to be from a representative or random sample. Nowhere in the problem stem did it say that they did a random sample. They just found 450 people with cardiac disease. So the very best we could do is to assume that the patients were representative of all patients with cardiac disease. And that depressed patients are independent of non-depressed patients. So we've got a random representative component and our independent group components rolled into one. So 2 checks in one there. Okay, then we would need to check to see if we have less than 10% of the population. So 361 and 89 are both fairly small numbers. So it's reasonable that 361 and 89 are each less than 10% of all patients with cardiac disease. Then we need to check our NPs and Qs. So N depressed, P depressed. Well, I don't actually know P depressed. I don't know the population parameter. All I know is one sample, which means I'm going to have to use a hat because that's all I've got. Okay, so I had 89 depressed patients, and it said that 26 of them died. Oh, well, they already gave me the number, right? So I know the successes, the number who died was 26. That's definitely bigger than or equal to 10, which means the depressed patients who didn't die, that's N sub D times Q sub D, is the rest of that group. So 89 minus 26 is the other 63 people in the group. That's definitely bigger than 10. Okay, let's look at the non-depressed people. So number of non-depressed times the proportion of non-depressed P hat N that died was 67. That's bigger than 10. And then N sub N Q hat sub N, so the number of people in that group who didn't die are the other 294 patients. That's definitely bigger than or equal to 10. So no reason to doubt the first condition or the second. Third works. All conditions are met. So yes, the conditions are satisfied. If I want to do a hypothesis test, I've got to name it. So we will use a 2 proportion Z test. Now, the mechanics are what get a little bit tricky. So I'm going to start with a picture. Okay, so because I'm at conditions, then this is a picture of all the possible differences in the proportion of depressed P hat sub N, or sorry, P hat sub D minus P hat sub N. So if I could find all the possible samples of depressed and non-depressed people, of 450 people, like what I took this time, this is what the picture of those differences should look like. In the middle of that is what we argued that difference was in our null hypothesis. In the null hypothesis, we argued that that difference was 0. There is no difference between the groups, is our argument. So that difference is always, always, always 0, because we're always going to argue that the two groups do not have different rates. Now what I have to do is see what the difference in our actual one sample that we have looks like, how different it is from 0, to see if I believe that this is true anymore or not. Now here's where things get really tricky. When I do the Z-score, the numerator is pretty much, it's a piece of cake. It's always the same. So we look at our 2 percentages, our 2 proportions from our sample. I'm doing depressed minus not depressed, so I want to do depressed people first. There were 89 depressed people, 26 of which died. So 26 over 89 is my sample p hat sub d from this one sample. And then I need to look at the difference of that and the non-depressed people. There were 361 non-depressed people, of which 67 died. So this difference is my new observed difference. So it's exactly the same as you would put at the beginning of your confidence interval. So instead of a single p hat, it's always the difference of the two p hats. We want to subtract that from the expected difference. The expected difference is always what's in the middle of this curve, which is the 0. It's always going to be 0 for a difference of two proportions. And then over the square root of, we need the standard error. And here's where things get really tricky. In the standard error formula, we're going to need the sum of two groups. The first group has 89 in it, the second group has 361 in it. So that part's the same as it was for the confidence interval. The numerators are going to be different, and this is where things get kind of weird. Okay, and the reason why is a little bit fuzzy. We could read about it in the book. I'm just going to skip to what you have to do. We have to actually pull our counts for those two groups to get our proportions for the numerators. So I'm going to go down here in the corner and I'm going to compute something called p hat pooled. So to pool means to put everything together in one group. So if I take the 26 people in the depressed group and the 67 people in the non-depressed group and I put them together, then I take the 89 people total from the first group and the 361 people total from the second group, and I put those two groups together to get a single proportion. Then that's, let's see, 93 over, can I add, I don't know if I can or not, 9 plus 1's 10, 15, 450, oh that's right, we had 450. So 93 out of 450 died. So this is the pooled proportion for all the people in the whole group that died. That's the p hat that I have to use in both of these numerators. Okay, it doesn't have to make sense why just yet. It just is how things work. So we're going to use that proportion for both. So 93 out of 450 is the proportion that died, which means the other, what's 450 minus 93? I don't trust my head to do that. 450 minus 93, I'll get it my calculator here, is 357. So 357 over 450 are the proportion of people who lived. And we're going to use that same pair of ratios in the second group. So the sample sizes, the group sizes, stayed separate, 89 and 361. The proportions of successes and failures, I'm going to use the same number for both of them. That's really weird, but that's what happens, and that's what the calculator is automatically going to do. That's a really ugly bunch of number crunching. So I'm going to finish it with my calculator. All right, so if I go to hypothesis test commands, so go to statistics. Number 7 is stat tests. And I have a 2 proportion z test down there on number 6. And I'm going to put in my two groups. So 26 people out of 89 in the first group, 67 people out of 361 in the second group. Then I have to pick what my hypothesis said. Was my hypothesis the first group's bigger than the second one, not equal to the second one, or less than? I had a greater than in my alternate hypothesis. So I'm going to pick the greater than and hit OK. Now the calculator automatically knows to pool these. If you look right here, you have a p hat without a subscript. That's your p hat pooled. If you crunch this 93 out of 450, it's actually 0.206 repeating. Okay, the z-score is 2.23. I'm just going to pull that right off the calculator. So 2.22. So that puts us 2 and a little bit more standard deviations above the mean about here. And I want to know the area under here. That's the p-value. So the p-value is the probability of a z bigger than 2.22. And the calculator has already done that for me. Okay, if I take another look here, the p-value is reported on the z-score, 0.013. So this is equal to 0.013, which is smaller than any normal alpha level, like alpha equals 0.05. So I'm going to reject the null because of that number. Okay, so I'm going to wrap that up in the next video.